Hi, thanks for being here. My name's Dara Goldberg. I'm a graduate student at the Scripps Institution of Oceanography, and I'm going to be talking about a collaboration between NASA, NOAA, and academic institutions where we're using the Global Navigation Satellite System Array, also known as GNSS or GPS if you're mostly American, and how we're using that to provide better local tsunami alerts. So first, let's get situated with this map of the world, which I've centered on the Pacific Rim, which you may know of as the Ring of Fire. And I've highlighted in red some of the major subduction zones in the world. And this is where we have thin, dense oceanic crust sinking beneath lighter, thicker continental crust. And it's at the interface between those two types of plate boundaries where we get the largest and most destructive earthquakes. And of course, since they occur under the ocean, we're also subject to very large tsunamis. And most of these locations have experienced a large earthquake and resulting tsunami in the past 100 years or so. And as they begin to populate the map, you'll notice that each one of them has also come with devastating effects to the economy, to infrastructure, and most importantly, loss of life. And of course, since I work in California, I'm particularly concerned with this region over here, which is in the Pacific Northwest of the United States, known as the Cascadia Subduction Zone. The last major earthquake to occur there occurred in about 1700 and was roughly a magnitude 9 earthquake. And the resulting tsunami was observed all the way across the Pacific Ocean in Japan. And we know from geologic evidence that we are pretty much due for another very large subduction zone earthquake at that location. So it's important that before that time, we can create realistic metrics to provide rapid tsunami warning to the local region in the Pacific Northwest, which is quite heavily populated. So what does ideally a local tsunami warning look like? So I'm going to invoke the example of the 2011 magnitude 9 Japan earthquake, which is the best corollary we have for what we expect in Cascadia. So on the left here is a kinematic slip model, and if we have long enough observation times and even longer computation times, we can create one of these models which shows us how slip occurred in both space and time during the earthquake. And using what we get out of this model, we can use the vertical deformation as input to a tsunami propagation model. And what that does is show us how the uplift during the earthquake affects the water column on top, and then we can see what the ocean waves will do. And that gives us useful information about not only what time the tsunami will arrive at the nearby coast, but also how large the amplitude of the wave will be. So I sort of alluded to the fact that this is not yet realistic in real time. This takes much too long to do in a real-time scenario and much too long in terms of observation times. This is more like the kind of tsunami warning that we get now. It's a basin-wide warning, and this is NOAA's warning from that same earthquake in Japan. But these are designed primarily for faraway regions like the Hawaiian Islands in the middle of the Pacific or even all the way to the west coast of Chile. But they aren't very reliable for the area near the earthquake. And going back to the example of the Cascadia subduction zone, we expect to have only about 15 minutes between when the earthquake arrives and the earthquake starts and when the tsunami arrives at the coast. So we don't have a lot of time. So what could we do for local tsunami warning in a realistic amount of time? Well, first things first, we can determine the location. We need to know, is it going to be offshore? And if it is, then we might be at risk of a tsunami. Secondly, we can figure out the earthquake mechanism in just a few minutes. We need to know if it causes significant vertical ground motion, because if the earthquake is only mostly in the horizontal direction, it doesn't disturb the water column in a way that we expect a destructive tsunami. And finally, we can determine the magnitude. We need to know, was it large enough to create a destructive tsunami before we issue an evacuation order? And it turns out that the magnitude is not only one of the most important metrics, but one of the hardest to constrain. And this is because of a well-known problem known as magnitude saturation. So large earthquakes are typically observed with strong motion accelerometers, so they measure accelerations. And in order to get magnitude, we have to integrate the accelerations to velocities and integrate them again to displacements. And that introduces this completely unrealistic drift that we have to filter out in real time. but unfortunately, once you filter them, it stunts the true amplitude of the displacement waveform, so it's impossible to tell how big this earthquake really was. So a magnitude 9 earthquake might look just like a magnitude 7.5, and if that's true, and we issue a warning for magnitude 7.5, we won't have the best evacuation order, we won't evacuate enough people. There is a solution, and that's with NASA-supported GPS. GPS is a land-based measurement that creates precise position estimates to millimeter precision. It gives us a reliable estimate of the permanent deformation after an earthquake is complete, but also a reliable estimate of the peak displacement during shaking. And it turns out that the peak displacement is the fastest metric that we can use to determine a reliable earthquake magnitude. So in this plot, here's observations from a bunch of large earthquakes in Japan. They're sorted by their source to station distance and the maximum displacement amplitude during shaking. And here you can see that these different magnitude earthquakes clearly separate out. So you can tell very clearly that this magnitude 8.3 earthquake is bigger than all the magnitude 7s, and it's smaller than the magnitude 9. And we can do that in about 2 minutes after the earthquake has occurred. So this is a really quick and reliable way that we can get to magnitude using GPS instead of traditional seismic sensors. So because we know that the GPS is so important, we've developed this collaboration with the NASA Jet Propulsion Laboratory, the Scripps Institution of Oceanography, and Central Washington University, where we are now sending real-time GPS data streams to the NOAA tsunami warning centers in order to help them figure out how large these earthquakes are in real time and issue rapid and reliable local tsunami warnings to the coastal regions near large earthquakes. Thank you.